guys, we're back, and this is probably the strangest lesson that we could throw at you, which I know sounds really scary, but it's the idea that numbers are made up. Yeah, I mean, think about it. Like, who decided that, this is called 7 for our language, and that we'll represent it with the symbol 7, and that's what 7 means. Like, it's all man-created, I guess. The concept of counting, made sense for us, and then we had to use symbols to talk about it and to write about it. And I'm not sure what I've shared with you so far. Hopefully I've given you some videos to watch that kind of gives you a history of like how numbers even existed, and that dives a little bit into what's called the different number systems, particularly the complex number system. So this diagram, which yes, I stole off the internet, shows you how our number system is kind of set up. So the real numbers are things that we are normally using in math up until this point. So 7, square root of 7, 3 halves, things like that. Those are all real numbers. And depending on how nice they are, they have different names. So the natural numbers are your counting numbers. Whole numbers are the counting numbers plus 0. And it's funny because it's just kind of like it progresses how you learn numbers as a child too, right, through school. So counting numbers, there's a 0, and then they talk about integers. Did you know numbers could go negative? That really blows kids' mind, by the way. And then rational numbers, fractions. And then we talk about, some things can't be written as fractions, like pi and square root of 3. Those are irrational numbers. But all of them are real numbers, which makes you think, what are you if you're not a real number? And this was a hard pill for the mathematicians to swallow back in the day. There could be another number system out there. And there's a whole documentary out there that I've probably shared snippets with you about, but if not, I'll attach it to this video too. Imaginary number system and how that thought kind of developed. Well, if we can have numbers, we can create a new number system that kind of works for us, and they can behave like numbers. It's wild. All right, so here's the basic idea. Not every quadratic we encounter has real solutions. We talked about the discriminant. If your discriminant is negative, those are not real solutions. So at some point in math, they accepted that there were things out there called imaginary numbers in the complex number system. And the idea is, if you would just accept this fact right here, the square root of -1 is a thing. Like, accept it. And because I don't like to write square root of -1, they said, can we just call it I? I think Euler was the one that came up with that part. It's like, ugh, so much work to write square root of -1. So they used I to represent it. Once you accept that, you can move forward. Well, that's nutty. All right, so I'm not sure, again, what videos I've shared with you, but before you start going, ugh, more numbers to learn about, this number system is what makes all electronics possible. All electricity, everything that you use that runs on any sort of battery power as well, has a circuit board. All of it uses the complex number system. So yay for all the dudes and dudettes in the past who came up with the imaginary number system. Okay, let's talk about how we can use this. So when we are breaking down radicals, just simplifying radicals, we talked about how to break it up into perfect squares and leftovers. But now today, because we're going to have negatives, you have to sneak in a -1. So use this pattern as we break things down. I'm going to use blue for perfect square. I'm going to use -1 in red, why not? And I'll use green for leftovers. So 9 is a perfect square, right? So when I break this down, and I put the 9 first, because he is a perfect square, there's also a -1 with it. And notice there's no leftover, so I don't need to use the leftover box. So now you start giving me better names. I have a better name for 9. The better name for 9 is 3. And then I apparently have a new name for the square root of -1, because it's just so hard to write the square root of -1. They're going to say, why don't you call that an I? And square root of -9 simplifies to 3i. Alrighty, let's talk about -6. So normally I would break it down using that pattern. But if I think about 6, there is no perfect square besides a 1. I guess you could put a 1 if you want to. But a 1, or you can just say forget it. There is no perfect square. Definitely have a -1. And then the 6 is what's left over. So the only thing I can simplify here is that we call the square root of -1 an I. And then the square root of 6, like, can't do anything with that, so we just write down square root of 6. So that is the simplification for that particular radical. And now let's talk about square root of -8. So this time we'll have all three parts. 8 is not a perfect square, but the perfect square as a factor of 8 would be a 4. Clearly there's a -1. And then the leftover part, it would be 4 times 2. So now it's the renaming step. The square root of 4 is a 2. The square root of -1 is an I. And then the square root of 2 is just going to stay as the square root of 2. So one year I was teaching, and I share this every year, and I wish I remembered what kid it was because I just love this. We were doing a whole bunch of these because he just was not getting it. And after like 12 examples of the same thing over and over and over again, he goes, it's like you just poke the eye out. All right. Sure. He's like, don't you get it? You like poke the eye out of the radical. And I said, okay. I mean, it's cute. It helps me remember, and I share the story every year because maybe it'll help you remember. So when you're taking the square root of something negative, in order to simplify it, you have to, quote, poke the eye out of it. All right, so what good does this do us? Now we're allowed to solve all of the quadratics that we were kind of stumped by in the past. Now we can solve them because we know how to treat the square root of -1. So for instance, we can go back and revisit how we solve by square rooting. I'm going to isolate the squared. I'm going to subtract 10 from both sides. So this now equals -36, and I'm not isolated yet. I got to keep going. Let's divide both sides by 3. So we have x squared equals -12. And now when I square root both sides, a couple of things I have to remember. I'm going to move my work over here. X equals, because I'm square rooting an equation, my solutions are both positive and negative. Remember that rule? So I got to put down a plus or minus. And now we got to think about breaking down that 12. So -12, excuse me, has a perfect square in it. It has a 4, has a leftover 3, and of course there's a -1 in the middle. So this is going to simplify to x equals plus and minus, rename this for me, 2i, and then square root of 3 just kind of stays. So really the only additional thing to that problem was the fact that we square rooted a negative number, so we, quote, poked the I out of it. That's not at all what we did, but you know what, whatever helps you. So now let's revisit my favorite, completing the square. What if I wanted you to complete the square on this problem? Well, you'd start by making sure this is a 1 in front of the x squared, which it is. And then you're going to shuffle the problem a little bit. And while we're moving that 30 around, I'm going to also add my blank. So remember, on completing the square, this constant needs to be subtracted or added to the other side. So in this case, it's subtracted. And then, of course, we got to balance everything out. If you added a blue blank to the left, you have to add one to the right as well. So what goes in that blank? This is that C thing, remember? So we take this middle term, so the coefficient, the 10, you're going to cut it in half, and then you're going to square it. So that would be 25, right? Again, these are my notes. I'm going to write down everything because that's just good habit. So why do we complete the square? Well, we complete the square because now this can be rewritten into a squared factor. So this becomes x plus, and then half of this term would be plus 5. Here we just add up the terms, so -30 plus 5 is 25 is -5. And then this is where our I is going to come into play. So we're going to square root both sides right now. This becomes x plus 5. I'm supposed to put down a plus or minus because I'm solving. And this is where I start thinking, okay, 5. No perfect square inside of a 5 besides a 1, so I'm just going to ignore that part. But I do have a -1, and I do have a leftover 5. So when it comes to renaming, this is going to be called an I, right? And I'm almost home free, guys. One more step. I'm going to subtract that 5 over. So x equals, let's see, -5 plus and minus I square roots of 5. You just gave me 2 non-real answers. If you wanted to separate them, you sure could. You could say -5 plus I square roots of 5. and negative 5 minus I squared to 5. So I don't care if you write them as one or if you separate them. Obviously, if you separate them, you're showing me that you really truly understand that you have two solutions there. But, you know, I understand if your laziness is overtaking everything else. I get it. Oh, that's a very tiny print, Abruzzo. Good news, we can now go back and do everything all over again, is what I just read. Okay, cool. All right, so that'll be a project for another day. Now let's talk about, now that we have this new number I, the square root of negative 1 is an I. We can treat it just like any other number, meaning we have what are called complex numbers, where we have a real part and we have an imaginary part. So a complex number looks like this, a plus bi. This guy here is the real part. This guy here is the imaginary part. And the number as a whole is called a complex number. I just love the English language. Hey Bob, what should we call this? Complex. Yeah, like that makes sense. Okay, so if I'm adding two complex numbers together, I want your answer written in standard form, which means it needs to look like that, a plus bi. You're going to add the real parts, and you're going to add the imaginary parts, and you're going to call it a day. So my real parts would be a 7 when I add them together. And then your imaginary parts, just watch your signs here. You got negative 1i plus 5i, so that's plus 4i. That's it. Done and done. That can't be bad, right? All right, so this next one, same idea. We got real parts that we're, oh, careful, we're subtracting this time. So 2 minus 3 is negative 1. And then be very careful on the imaginary subtraction because everyone forgets to distribute. So we have 8 and then a minus 12. So that's really a minus 4i for the imaginary part. And that is your final number. That is the complex number in standard form. All right, we're going to multiply next. And there's a little note up here about you need your answer in standard form when you're done. So it has to look like this, a plus bi. And there's a very important clue over here. If I equals the square root of negative 1, if you were to square both sides of this equation, you would end up with this. So anytime you see an I squared, you can swap it out, replace it with a negative 1. That's going to be very important in these multiplying problems. Okay, so you can multiply real numbers and complex numbers together. It doesn't matter what kind of numbers they are. So this becomes, let's see, an 8i, and then a plus 10i squared. Well, guys, that doesn't look like a plus bi. So I have to come through and remember that statement that we just highlighted. I squared is really a negative 1. So this right here really says 8i, and then 10 times negative 1 is really a minus 10. Technically, this is the right answer. If it bothers you that it's backwards, then just flip it around. Okay? There's a plus bi form. The real part is now negative 10, and the imaginary part is the 8i. Oh boy, this one's fun. Feels like a foiling problem, doesn't it? That's because it is. All right, 3 times 3 is a 6. And then we've got 3 times 6i, so plus 18i. And then negative I times 2 is negative 2i. And then negative I times 6i is a negative 6i squared. So, yeesh. All right, these are like terms. So at the very least, I can combine those. And then we just talked about this I squared thing. It's something. So we have 6. I'm going to combine these and say plus 16i. And then a negative 6 times a negative 1 is really a plus 6. So we're still not done because now you've got these like terms, these real parts that can add together as well. And now we're done. We have a 12 plus 16i. So I guess the moral of the story is you can't stop doing these questions until you get your answer in standard form. So just keep working until you got that. 11 is a very special problem. We'll talk about it in a minute, but let's go ahead and distribute. 4 times 4 is 16. 4 times negative I is negative 4i. Positive I times 4 is positive 4i. And then positive I times negative I is negative I squared. So again, a couple of things we got to consider. We have some like terms right there that are actually going to cancel out this time. And then we have to remember what I squared is. I squared is really a negative 1. So you've got a 16, and then these are canceling. And then you have careful, a subtract -1. So what you really have is a +1. Ladies and gentlemen, you just multiplied two complex numbers together and you got a real number answer. That happens. These are very special. They are called complex conjugates. If you go back and look at the original problem, you'll notice that they are good twin, evil twin pattern. We've done a lot of factoring with those types of patterns before. So if you see that with complex numbers, they're always going to multiply together to produce a real number at the end, which is kind of amazing, and we're going to need to use that in a minute. Oh, number 12. Everybody gets this one wrong on the SAT because they think they're just supposed to square things. But 7 plus I squared is really a 7 plus I times another 7 plus I. So it is a foiling question. Now these are not conjugates, so don't expect that cool all that simplification that we saw in the last question. 7 times 7 is 49. And then we have a plus 7i with another plus 7i. And then I times I will be plus I squared. So same idea, simplification. We're going to collect our like terms right there. And then we're going to remind ourselves that I squared is really a -1. So we have a 49. We got a plus 14i in the middle. And then plus -1. That's goofy. I'm just going to say -1. And then, of course, still not done because then I got to come back through and collect these real parts. So this is a 48 plus 14i. There is your real number, or sorry, your complex number in standard form. So there's only one left, right? Dividing. Now, I don't know about you, but when my teacher gives me this much space on a worksheet to do a question, that makes me very nervous. Yeah, me too. You can't divide by I, because someone in math said it's not okay. So I is really the square root of -1. There's some rule out there that says you can't have a radical in the denominator of a fraction. So in order to divide by I, we have to use a complex conjugate. We just talked about that, right? So the complex conjugate is the good twin, evil twin idea we just talked about. So the conjugate to the denominator is going to look exactly the same. The only difference is when you find the I part of the term, the imaginary part of the term, you need to give me the opposite sign. So instead of 2 plus I, your conjugate is going to be 2 minus I. And we know from 5th grade that I'm allowed to do this as long as I do it to both the numerator and the denominator. So here's what you got. You got two multiplication problems. You're going to need to multiply this together, and you're going to need to multiply this together for the denominator. It's not as bad as it seems, but I don't want you skipping steps, okay? So up top in the numerator, 8 times 2 minus I, if we distribute that 8, we'll get a 16 minus 8i. Just walk away from that for a minute. Down in the denominator, we got these conjugates, and we know something cool is going to happen with the conjugates, but for your notes, don't skip any steps. So 2 times 2 is 4. Then we have a minus 2i. Then we have a plus 2i. And then I times negative I is negative I squared. So the numerator isn't doing anything. We're just going to keep it as 16 minus 8i. But your denominator has a little bit of work to do. First of all, these like terms in the middle, they're going to cancel out, which is what conjugates are supposed to do. So you should see that. The other thing that we're going to have to fix is reminding ourselves that I squared is really a -1. So down here in the denominator, you've got a 4 minus a -1. So y'all, we got a 5 down in the denominator. Now for Algebra 2, I don't think there's anything wrong with you guys getting here and stopping. I'm actually okay with that. But what you should be doing is taking this 5 and dividing it underneath each of the real part and the imaginary part to get the complex form. So 16/5, that's your real number. And then minus 8/5 I, that's the imaginary part. So if you're asking me which one I like this one better because it does say in standard form right here. But for Algebra 2, if you didn't get that far, I'm okay with that. Precalc, I care. So if you're coming on to Precalc next year, remember. Oh boy, same idea, guys. 5 plus 3i. I need to figure out the complex conjugate to that. So you don't change the 5. What you do change is the sign for the I term. I think I just said it wrong. Okay, so 5 plus 3i is the conjugate. Now this one is a little more exciting than the last question because your numerator is also a complex number. So the foiling in the distribution is a little more complicated. It's a bummer. The good news is I think this, oh, there's one more question after this. So we're almost done. Okie dokie. So I'm going to FOIL this baby out. And trust me when I tell you, you should not skip steps on this. It's very easy to mess up. All right, 5. And then outside here would be plus 3i. The inside term is plus 20i. And then 4i times 3i is a plus 12i squared. We got a lot of simplifying to do there, but not yet. Just write it out. Okay, green conjugates. I know stuff is going to cancel, but I'm not going to skip steps. So we got 25. We have a plus 15i. On the inside, you have a minus 15i. And then negative 3i times positive 3i is a negative 9i squared. Okay, a couple of things happen. We got like terms right here. We got like terms here, but even better, they're going to cancel. We've got some I squareds that are going to need to trade out for negative 1s. So up top, we've got, let's see, a 5 plus 23i, and then 12 times negative 1 is a minus 12. Down in the denominator, we've got a 25. Those middle i's canceled, and then negative 9 times negative 1 is a plus 9. All right, we're almost home free. If I were to add together these real parts, I have a negative 7 plus 23i, and then of course my denominator is a 34. I'm okay with that answer, but I'd like you to keep going. So if we divided each of the real part and the imaginary part of with the 34, now you can see the answer in standard form. In the next question, we'll talk about why standard form is so important, but standard form is what they really want to see, okay? Speak of the devil. All right, so when you have applications of the complex number system, it's usually in reference to electricity and circuits, among other things, but each component of your complex number refers to some component of the circuit. So they're using different notation because when you start mixing math with science, people start using variables that make sense to their application of the math. So just be flexible with your variables. So we got a circuit. It's created with several components: resistors, inductors, and capacitors. So the overall resistance of a circuit is referred to as the letter Z typically. And then overall impedance can be found by adding up all of the components together. Cool. Each resistor is a real number, R. So you'll notice on the formula here, the resistors don't have any i's with them because they're real numbers. The inductors are imaginary numbers that are pure, meaning they don't have a real part, they just have an imaginary part. So Li. And then a capacitor has a negative value in front of it, and they refer to that as C times I. Again, another pure imaginary number. So it's been a long time since I talked about like electricity work. I have a very shallow understanding of it, I guess. But the idea is, depending on where you want your electricity to flow, some things push the circuits, push the electricity through the circuits, and some block them. So you want to make sure that your overall impedance of your circuit is where you want it to be. Because you can like blow a circuit, right? I've done that. That I know about. So the overall impedance is what we're trying to find here, guys. So Z equals the resistor. And this symbol, by the way, is ohms. It's how they're measuring the electrical current. So the real part is 6. And they just want you to take that number and write it down. And then the inductors are the L, right? Yes. So L with an I after it because they're imaginary. So that in this case it'd be 10I. And then normally I'd say plus, but it's negative, so it's kind of weird. But so negative 5I. And the only thing as a mathematician that I can do now is simplify this. So the overall impedance is 6. And then if we're adding up this imaginary part, these imaginary parts, we get plus 5i. So there's your overall impedance. Again, that's going to be taken to another level in their calculations for whether what this means for the circuit itself. But that's how they would calculate the overall impedance. So same idea here. Overall impedance, we got a resistor of 13. Now this time there's 2 inductors. I was just going to say there could be more than one, so here you go. They got a 4 and a 5. So you can go ahead and add them up and call it 9, or you can just separate them. It doesn't matter what order you do this in, but I'll go in the right order of the problem. So 4i plus 5i. And then we're going to take away the capacitor, so 7i. So we're just going to simplify what we can as mathematicians. This is 9 minus 7, so that's 2i. So your overall impedance is 13 plus 2i. Ohms is the label on this, but I'm not labeling it for some reason because I'm being naughty. All right, so complex number system. It's a huge idea in math, and it really opened up all of these branches of mathematics that makes everything possible that you guys love. You know, things that you love to spend your time doing, playing video games, playing on your cell phone. Anyone who's going into electrical engineering or being an electrician in general, you do have to work with the complex number system. It's a really large part of your training. So I know sometimes we learn things and you're like, I never need to know this. Like, you might. So this is kind of cool. And the idea that numbers are made up is kind of mind-boggling. But that's really kind of true for all of math. It's all man-created to explain how nature works. Ooh, that was deep. All right, good luck, everybody. I'll see you.